And hopefully with those puzzles, it will help you to understand what those edge cases are and how you can use them in a safe way. My name is Simon Ritter. I am the Deputy CTO of Azul. So quick show of hands, who's heard of Azul? Okay, a few people, but not everybody. Well, I have one slide at the end, which is my sort of marketing slide, and I will just very briefly mention what we do as a business right at the end. Firstly, some fundamentals about pattern matching. What do we actually mean by this? We're not talking about patterns as in regular expression patterns. What we're talking about here is a technique that's been used right from really the very beginning of programming languages. You go all the way back to the 1960s, and if you look at languages like Haskell and Awk, you will find pattern matching being used. Just as an interesting thing here, how many people have used Awk? AWK. Ooh, a few people, right? Well, what we mean by a pattern in this sense is something which consists of two parts. The first part is called a match predicate. And a match predicate is essentially something that evaluates to a Boolean, true or false. So it's like an if statement. And based on the match predicate, this is going to determine whether our pattern is going to match against a given target. This will all become clearer as we go through, but it's useful to set the kind of baseline as to what we're talking about. Now, in addition to the match predicate, we're going to have 0 or more pattern variables. The pattern variables are going to be extracted conditionally based on whether the pattern matches the target. So that's what we mean by a pattern, a match predicate, and then a set of pattern variables. Now, before we get into pattern matching, we need to talk about a couple of other things which have been introduced into the Java programming language over the last few years, because they influence heavily how pattern matching works. The first of those is switch expressions. If we look at the way that the switch statement works in Java, it was taken from the C programming language. The syntax is exactly the same. C, as a programming language, has been developed really for systems programming, so compilers, operating systems, and so on. But the reality when you look at the way that the switch statement works is that it has some things that make it a little bit more error-prone than we would like. What do I mean by that? Well, the first is that when you have a set of cases, you can have some code associated with that set of cases, and you have to remember to put a break statement in. If you don't put a break statement in, it's perfectly valid syntax, and it will just drop through to the next set of cases and then do whatever they are set up to do. So let's have a show of hands. Who here has ever forgotten to put a break statement in with their cases? Everybody, yes. And we know that leads to difficult to find bugs, because you think, it can't do that. I've got this value, and I can't possibly get to that bit of code. And then you notice that you don't have the break statement, and it's like, okay. There's also some interesting things around the way that local variables work with this that's not necessarily intuitive. So if we look at an example of a switch statement, this is a very common way that we use it. What we're doing is switching on one variable, in this case, the day of the week, and we want to assign a value to another variable, in this case, the number of letters. Clearly, we've got simple code here which does switch on day, case Monday, case Friday, case Sunday, number of letters is 6, and then remember to put the break statement in. And then we do the same thing for the rest of them. And if we've got something we don't recognize, we put in a throw statement. Now, what they did in JDK 12 was introduce the idea of switch expressions. Now, switch expressions ties up a lot of the issues that we have with switch statements. Firstly, we are returning a value. So we only make the assignment once. That's very good, because the compiler can make the necessary checks for us to make sure that in all of the cases, we either return a value or we have a new thrown exception. So this is good. We can catch more errors at compile time. The other thing you'll notice from this is that the code is a lot shorter than on the previous slide, and yet we haven't lost any of the readability. The reason for this is that the developers of this feature discovered this little-known technique It's called a comma-separated list. Now, finally, we can have case Monday, comma, Friday, comma, Sunday, all on the same line. No requirement to have 3 separate cases. Then we borrowed some of the syntax from Lambda expressions. We used an arrow, and the right-hand side of the operator is the value that we're returning. Great. Now, switch expressions must be complete or exhaustive. And what I mean by this, we'll come back to later. Second thing we need to talk about is algebraic data types in Java. And if you were here for Ben Evans' talk earlier on, this is going to seem familiar. So I'll kind of move over this fairly quickly. But essentially, what we're talking about here is a couple of things. One is that in Java, we create a lot of simple data classes. What I've got here is your classic point. In order to have a point with 2 values associated with it, double X and double Y, I've got to create a class, I've got 2 instance fields, then I've got a constructor with values that I pass to it, I've got to explicitly assign the values from the parameters passed to the constructor to the instance fields, and then because they're marked as private, I need accessor methods to get the value of X and Y. 14 lines of code, all to create a tuple. Now, I've always thought that in Java, we have a class for pretty much everything. Why don't we have a class for tuple? And I asked Brian Gertz about this, who's one of the architects for the OpenJDK. And he said, well, yes, we could give you a tuple class, but then you'll want a triple and a quadruple, and where does it stop? So the solution that they came up with was records. JDK 14, we introduced the concept of records. What we're doing here is creating a way of specifying a data type with a simple declaration. Essentially, what we've got here is a class. It's just the way we declare it is slightly different, and so it's a special form of class. You can think of it like enumerations. Enumerations are still a class, they're just a slightly special form of class. The nice thing is that rather than having 14 lines of code and lots of boilerplate, I can simply say record to indicate it's a record, point, and then use the same syntax we have for the constructor to say that what I want to store in that record is a double X and a double Y. All of the rest of the code is generated by the compiler. Now, because it is a class, we still have the braces, but we don't put anything in there because there's no extra functionality. We can make our records generic if we like, so we can add a generic type parameter, store something of anything of type T, and do the same thing. If we want, we can add more functionality. It's a class, so we can still add new methods to provide different behavior, and we can have static instance fields. We can't add any instance fields that are not part of the record declaration, but we can have static instance fields. So in this case, I can declare pi and then have a method that calculates the area of a circle. The other thing that we need to consider is the way that inheritance works in Java. If we look at the way this has behaved previously, we have the ability to have a type hierarchy like this. Java's object-oriented, so we have inheritance. Shape is our superclass, and we've got 3 subclasses, triangle, square, and pentagon. All good. The problem with this is that we're very restricted in how we can allow access to our types. If other people want to inherit from shape or square or pentagon, then they can do that. The only way we can control that is by marking a class as being final, in which case no further subclasses can be made. But that kind of leads to some issues. And so in JDK 15, they introduced the idea of sealed classes. Sealed classes now says, okay, we want to have a class called shape. We'll add an additional modifier, sealed, and then we'll have a permits clause, which says the one classes that we want that are going to be permitted as subclasses, triangle, square, and pentagon. So this is all good. If somebody comes along and says, ooh, I like that shape class, I want to inherit from it and make a circle, the compiler is going to reject it. It'll simply tell you that you can't extend a sealed class because the class you're trying to create is not listed in the permits clause. Right, so let's get on to the pattern matching side of things. The first thing that was introduced was the idea of pattern matching for instance of. If we look at the instance of operator and the way that it works in Java from the beginning, again, because Java is object-oriented, one of the features of object-oriented languages is polymorphism. Polymorphism says that when we view an object, we can view that object as any of the types which it represents. That's the concrete class that it actually is, any of the supertypes of that class, all the way up to object, any of the interfaces implemented by that type, whether they're from the concrete class or any of the superclasses. Now, if we want to actually view an object as a specific type, then we need to do a cast. And in order to do that safely, we use instance of to determine if the reference actually is of that type. We end up with code like this, which is very common. We say if obj instance of string, so we're looking to see if it represents an object of string type string. If it is, then we have to do this explicit cast and assignment. We create a new variable called string s, and then we assign to that obj but cast as a string. And if you look at that, you kind of think to yourself, well, why do we have to do that? If we've done a test for instance of obj and we've confirmed that it actually is a string, why do we need to do that explicit cast? Surely we can just treat obj as a string in the true branch because we know it is a string. And that's one way of solving the problem. It's not the way they solved the problem, though. What they did was introduce pattern matching for instance of. And this was in JDK 14. So now what we do is we say, if obj instance of string, if we go back to the pattern matching definition I gave you at the beginning, that's our predicate. So remember, predicate equates to true or false. Obj instance of string says, is this an object that refers to a string? Yes or no, true or false. If it is, we have a pattern variable, s, which is going to be conditionally extracted. So it's extracted if we have a reference to a string. In the true branch of that expression, we can refer to s because we know that we have a string. In the false branch, we've failed the test, so the scope of s is not valid. We can't refer to s because it isn't a string. Now we can take that further, and we can say if obj instance of string s and s.length is greater than 0. We can do this because we know that in the AND operator, we always evaluate the left-hand side first, and only if that evaluates to true do we evaluate the right-hand side. So if we evaluate the left-hand side, it's true, we do have a string, the scope of s is valid, so we can simply say s.length, test that to see if it's greater than 0, and that will work. If we try doing the same thing with an OR operator, that won't work because, again, we know that the OR operator, we always evaluate the left-hand side, and only if that evaluates to false do we evaluate the right-hand side. If it evaluates to false, we don't have a string, so the scope of... Yes, don't think I need to be aware that I'm having a team meeting in 15 minutes. And only if we evaluate the left-hand side, only if that evaluates to false do we evaluate the right-hand side. But if it evaluates to false, we don't have a string, so s is not valid in scope, and we can't call the method on it. Now, we have to be careful with the scoping of our pattern variables, because we could invert the test. So it's not always the case that in the true branch, we have s as being valid. We could do this, and we could say, if not O instance of string s, return. And that means that the scope of s is valid for the rest of that method because we've inverted the test. Which then brings us to some more details about the way that the pattern variables work, which is that they use flow scoping, how you define the scoping of a pattern variable. If we look at local variables in the Java definitions say that the scope of a variable is from where it's declared to the end of the block in which it's declared. Now, that could be a method, it could be a for loop, a while loop, or even a set of braces to indicate a separate block of code. Other thing about local variables is that they're subject to definite assignment, meaning that they have to have a value associated with them. Unlike instance fields, there's no default value for a local variable. With pattern variables, the definition is that the scope of a pattern variable is all the places where it is subject to definite assignment. So all the places where, when you match the pattern, that variable will have something associated with it, and therefore you can use it. That means that when we inverted the test, the place where it had definite assignment was after the test which we'd inverted and returned from the method. So the rest of the method was where we had definite assignment. So it does mean that we have slightly different rules in terms of scoping, and that allows us to do some different things. So for example, we can do this. We can say if O instance of integer num, so we're using the pattern variable num, and then we can say else if O instance of float, and reuse the pattern variable num. I couldn't do that with a local variable, and we can do the same thing with instance of long, reuse the same pattern variable, and that will all work. That relies on us using flow scoping rather than local variable scoping. Now, this brings us to my first puzzle, and this is where we get some audience participation. So in this puzzle section, we're going to ask you to vote. So show of hands as to what the result is. I have here some code. So I've created a new object reference and I've called it S. Then I've got if S instance of string, that's my pattern predicate, but then I've also used S as my pattern variable. If I've got a string, I print out string of length. If I haven't got a string, I print out no string. So I'm going to give you 3 options as to what the result of this is. Option 1, the code will work. Okay? Option 2, the code will not compile. Fine. But I'm going to give you a third option. And the third option is the code will not compile, but it will work. Aha, right. So who's going to vote for option 1, the code will work? Okay, a few people. Who's going to vote for option 2, the code will not compile? Okay, looks like quite a lot of people. And who's going to vote for option 3, the code will not compile, but it will work? I don't see many people there. Okay, a few people on the right-hand side. Well, the answer is the code will not compile. Right, fine. So the code will not compile if we use Java-C. Because what's going to happen is the compiler will quite rightly say that we have already used variable S as our object reference, and we can't reuse it for our pattern variable. So you would think to yourself, well, okay, that's not very exciting, is it? I mean, you've just proved that the compiler does what we expect it to do. Haha. Except that it does work. Because if you use JShell, it will actually work. I've literally cut and pasted from JShell here, and I tried it with JDK 23 to make sure that the latest version of Java does this. Object S, new object, great. Then if we do if S and all of the rest of the code, and we get no string. I have no idea why this works. Absolutely none. And more than that, I have actually talked to some of the engineers at Oracle who work on this, and every time I show it to one of them, they go, that shouldn't do that. And it's like, that's a bug. I'm going to take a photo of it. Yes, I should file a JShell bug. But I like to use it in my presentation, so I'm not filing a bug yet. Right, moving on. Pattern matching for switch. If we look at the switch statement and even the switch expression, or the switch statement, we are limited on what we can switch on. So initially, we could only switch on integral values. Then we introduced the idea of being able to switch on strings, and we also allowed the idea of switching on enumerations. What we've now done is to extend this so that we can switch on type patterns as well. And we can do something like this. So we can create a type tester, which takes an object reference, and then we'll switch on that, and we'll have different cases for the type of the object, not its value. First one we're going to have is case null. So we have a case where if we've got a null reference, we can handle that and actually print out a message. Then we have a case for string, and we'll have a pattern variable associated with that called S. Since null is a constant, we don't need a variable, it's a constant. So With string, we can have a pattern variable and print out the value of the string. We can also have a pattern for color with a pattern variable C. Now, primitives in Java are not strictly types. So we can't treat them as objects, but an array of primitives is. So we can have case int array, IA, as the pattern variable, and then print out the length. And then we can have a default as well. So, interestingly, some details about null, because previously we haven't had the ability to include a null in a case. You have to have a separate test outside of the case to say, is the reference we're dealing with null? And that kind of makes the code a little bit less nice to look at. So it's good that we can include that now into the switch itself. But there are a couple of things to say about that. The first is that the way it works is that the compiler has been changed so that to maintain backwards compatibility, if you don't put a null case explicitly in your switch, one will be inserted for you. And that will throw a new null pointer exception. The reason for doing that is because they also have said that the default doesn't catch a null. So you wouldn't catch the null through the default. What that means is that if we take the same code we had before and we leave out the case explicitly for null, what the compiler is going to end up compiling for you is inserting a case null, throws a new null pointer exception, and your behavior is exactly the same as you would have expected it to work in the past. The other thing you can do is you can combine null with default. Even though default doesn't catch null, you can say, I want to handle them in the same way, and do that explicitly by putting them as comma-separated values for the same case, and say, okay, we've got bad input there, do whatever. Now, the other thing is completeness. So I mentioned this when we were talking about the switch expression earlier. What we have with pattern matching for switch is the need to match against all possible types. If I have this code here, so I've got a case string, and I've got a case for integer. What happens if I pass a float or a color or some other reference in? Well, you could argue that you could treat the switch as if it's a multiple if-then-else kind of construct, and because there isn't a case for whatever object you passed in, you simply ignore it and move on to whatever's below the switch. But that's not the way the designers wanted it to work. They felt that was too error-prone, so they said it has to deal with all possible types that you can have. In this case, to do that, there's an infinite number of types. So you can't simply list out all the possible types. To get around that, all you do is add a default. That way, case integer, you do one thing, case string, you do another thing. Anything else is handled by the default. That doesn't mean that you actually need a default for every switch. This is where we come back to the idea of sealed classes. Taking the example we had before, where we had a shape, a triangle, a square, and a pentagon, we can construct a switch which has a shape. So then we do switch on shape, and we say case triangle, case square, case pentagon, case shape. That covers all possible types that we could pass to it. There is literally nothing else we can pass in that sealed type, so we do not need a default in this particular situation. Now, guarded patterns are something that was introduced. They weren't actually introduced in JDK 19, they were introduced in JDK 18, I think it was. But one of the things that they did was they changed the way that they designed it. So in JDK 18, the idea of a guarded pattern was to say you match on a type, and then in the same way that we saw with the instance of pattern, you can add a conditional part to it and say, if we match this type and some expression evaluates to true, then we want to do this. But the way they did it prior to JDK 19 was in the same way that you would do with instance of, using an AND operator. Then in JDK 19, they said, let's not use the AND operator. Let's introduce a new keyword, when. And that way, we'll make it more readable. So we'll say so a case triangle T, when T.area is greater than 25. Yeah, I guess you can sort of say that it's a little bit more readable. But as we will see, this actually introduces some very interesting situations. So we have our guarded pattern, and case triangle T when T.area is greater than 25, and then we can also have a case for triangle on its own, which is where we've got something which is less than 24 or less than equal to 25. So a guarded pattern is essentially your primary pattern when, and then the conditional and expression. Only works with patterns, so you can't do a constant when something else. Sort of puzzle too. This one's not quite one that requires you to vote on it, but it's more a sort of explanation, shall we say. Confusingly guarded patterns. So let's start with our sealed class. We're going to make it abstract. We're going to call it interrogator. And this is going to have a number of subclasses which are who, what, where, when, and why. So we're then going to create a class when, which extends interrogator. So this is just the definition of the when class. And we're going to include in that a method called when, which returns a Boolean. What we can then do is something like this. So we create a test question method that takes an interrogator, and then we'll switch on that question, and we'll have some cases associated with that. So we're going to have a case what with a pattern variable name what, and print out what, same for where and same for why, and then the default, which should never happen because, well, it's a sealed class, so you shouldn't be able to do that. Well, technically in that case you can. So then we'll add case who, what, when, where, why. And we can do that because this is a guarded pattern. So we can say who is the class that we're matching against, the type, what is the very badly named pattern variable, when is the fact that we are using a guarded pattern. And it's important to understand that the when is not used as a reserved word. It is used as what's called a contextual keyword, meaning it only works as a keyword in certain places. That place being when you've got a guarded pattern. And then where is the method we're going to call, and why is the method we will call if where returns true. So then we can get really silly. And we can do case when. And the question is, explain what when means, where, and why. So if we break this down, essentially what we're saying is that the first when is the pattern type that we want to match against, so the when class. The second when is the pattern variable that we're going to use. So this is more in keeping with what we should have. And then we're going to have the third when is the contextual keyword that indicates we have a guarded pattern. The fourth when is where we say that that's the pattern variable that we're going to use on the right-hand side of the guard to evaluate whether the guard matches. And then the fifth when is the one that indicates that's the method we're going to call on that variable to determine true or false. And then if it evaluates to true, the sixth when is what's going to be called locally because the guard evaluated to true. I do not recommend programming like this. Not good. Okay, puzzle number 3. Right, we're going to use our sealed class again. And we're going to say, okay, public sealed class, shape permits triangle, square, pentagon. Now we're going to have a shape tester, which takes a shape, and we're going to change it around a bit. So I've got case shape, case triangle, case square, case pentagon. So what's wrong with this switch? Yes, okay, so I think I can hear the right answer down below there, which is, the problem is that shape is the superclass of triangle, square, and pentagon. And that means that everything that is a triangle, a square, or a pentagon is also a shape, polymorphism, which means that the compiler will say, oh, no, you can't do that. This case label is dominated by the preceding case label. It would actually be the triangle which is dominated. And what it means is that the code below the shape case is unreachable. There is simply no point in having those cases because everything will match against shape, and so we need to rearrange our types so that we don't have pattern dominance. But we also need to be careful when we're using guards. So if we put case triangle t first, print out a big triangle, case triangle t when t.area less than 25 as the second case, then we'll get the same problem. The compiler will catch that, and it will say you're having an unguarded pattern dominating a guarded pattern. Everything that's a triangle will match first against triangle, and we'll never get to the one that has a guard, so it will never be evaluated. That's good, so we're catching errors at compile time rather than at runtime. What about this? If we have two guards where we say case triangle t when t.area is less than 100, and then we'll have another one which is case triangle t when t.area is less than 25. Well, anything that's less than 25 is also going to be less than 100, isn't it? So you kind of think to yourself, what happens here? Well, actually, this is fine. The compiler only cares about type dominance. It doesn't care about specific guards. It's not clever enough to look at those individual guards and say, well, hang on, if you're looking at less than 100, everything will be caught by that guard, and it will mean that the second line is unreachable. So the compiler can only do so much for you. In this particular situation, it will not be able to tell you that the second line of code is unreachable, and you just have to live with that. What we could also do is we can remove the triangle completely. So remove the triangle case and only have two guarded cases for a triangle. What happens now if we call shape tester on new triangle 200? Anybody guess? Shape, thank you very much. Yes, of course, because the triangle is still a shape. So even though the guard doesn't catch, the guard is not catching it in either of those two cases where we have a triangle explicitly, it will still be caught by the shape, and therefore we maintain that completeness for the switch. Record patterns. So pattern matching instance of and records. We can do pattern matching with instance of, and we can use a record in exactly the same way that we can other classes. So we could do something like this, where we've got our record, point double x, point double y, and we can say, if O instance of point p, so our pattern predicate is O instance of point, and we can then have a pattern variable p, we can then extract the values from our point by calling the methods on p, assigning them to local variables, and then calculating the hypotenuse by doing Pythagoras. This is good, but we can do better. And we can do better using record patterns. Record patterns were introduced in JDK 19. This is an example of a deconstructor pattern, where what we're doing is not just matching against the predicate and assigning something to the pattern variable, we're also extracting values from that reference and assigning them to some different variables. Now again, deconstruction patterns at the moment only work with records. Now what we can do is something like this. So we can say, if O instance of point double x double y. We can use the record declaration, as we've used elsewhere, put that into our pattern that we have for instance of, and this will now assign the values of the points x and y values to these variables called x and y. One of the things that's important to get across here is that you do not have to use the same variable names in the record declaration as you would have done when the record was declared externally. So you can use completely different names if you want, just so long as you have the right signature for the record declaration, everything will work as you expect it to. Now what we can do is we can say, simply use x and y without having to extract the values explicitly. Now, the other thing is that when we had JDK 18, where we're using the and rather than when, they would allow you to have a pattern variable as well as a record deconstructor, technically. But this is not allowed now. It can introduce ambiguous situations for the compiler. So you can do this quite happily, where you say, O instance of point, the predicate, assign the value of point to p, and use that. What you can't do is have O instance of point double x double y, where we're doing the deconstruction, and have a reference to P, where you might want to use it separately in your code later on. That will not work because if you call your pattern variable when, and then you try and do the kind of guarded thing that I did before with using when, then you run into a situation where you have an ambiguous situation where there are two different ways of interpreting the code, both of which are completely valid, but the compiler cannot disambiguate between them, and so they decided we'll just drop the idea of having pattern variables associated with records when you're using a deconstruction pattern. Now, patterns are also composable. So let's put some code together. Firstly, we're going to have an interface called rectangle, just to make life easier. We're going to have our point again. Now we're going to introduce an enumeration for color, red, blue, and green. And then we're going to have a couple more records, one which is color point, which takes a point and a color. And we'll have a color rectangle, which takes two color points, top left, bottom right. And to make my life easier, we'll also implement rectangle. So now we can do this. We can say print the color of a rectangle. And we can use our deconstruction pattern, and we can say if our instance of color rectangle, give the record declaration, so color point top left, color point bottom right, and print out the color of top left by calling the C method on top left. Great. But we know that top left is a record as well. So let's use deconstruction on that. So now we can say if our instance of color rectangle, color point, point P, color C, color point, and then because to make the slide easier to look at, I'll just rename the second variable BR rather than bottom right. And now we can print out C. Aha. But we know that point is also a record. So let's get really silly and go print top left X of a rectangle. And we'll say if our instance of color rectangle, color point, point double X double Y, color C, color point BR, print out X. And you start looking at that and you think, well, that's all very well and good, but I'm starting to lose that readability that I like in my code, and it's getting more and more complicated. There are two ways that we can simplify this. First is we can use local variable type inference. Introduced in JDK 10, we can use var rather than having explicit types. And we can simplify things by saying color rectangle, color point, point, var x, var y, var c, var br. And then it's slightly easier to read, even though it's actually less understandable because you don't know what the types are. But then in JEP 443, they introduced the idea of unnamed pattern variables. What this does is allow you to match against something, but not care what it is, which kind of seems a bit counterintuitive when you think about it, but it actually makes sense. You're looking at something and you're saying, I don't care what it is. So this uses the single underscore character. Single underscore used to be valid as a variable name, except nobody would ever do that, would they? No, not using a single underscore as a variable name. Then JDK 9, not 19, JDK 9, they made a single underscore a reserved word. If you are really determined and you really want to use underscores as variable names, I checked, and 2 or more underscores will still work. So you can use 2 or more underscores as a variable name. But now what you can do is this, and you can say our instance of color rectangle, color point, and then the thing that we're actually interested in is obviously the point, so we maintain the information there, and we have var x to indicate that we're interested in the x. That's what we want to use in the body of our code. But the rest of it, we don't care about. So we don't want to know what the type or assign a variable to anything for the y component or the color component or the bottom right component. And that simply says we know something has to go there, so the compiler can match against the signature, but we don't actually care. We'll use a single underscore to indicate its presence, but not what it is. So, got no interest in those, just ignore them. We can also use this with the pattern matching for switch. Because you need a pattern variable in your case, so case string, you can replace that if you don't want to use it with a single underscore. That's probably less valuable because you can just put a random character in there and it's not going to really lose any readability. But you can do this if you want. Last thing to talk about is primitive types in patterns. So I said that previously you couldn't use a primitive in a switch pattern matching. You could use an array. Now what they've done in JDK 23 is to extend things so that you can use primitive types in patterns. And this applies to both instance of and switch. So now we can do something like this. We can say byte x equals 128, and then we can say if x instance of int, then we have an int. If x instance of int as the pattern predicate and include a pattern variable, I, then we can print out we have an int with a value of I. We can also get into some rather confusing situations. We can add things where we have both constants and types involved, and we can include guards as well. Here I've got a simple example, where we say float new value equals switch on value, and then we can have case for 0, where we're going to return 5, case for float x, where x equals 1, and then return 6 plus x, or case float x on its own, and return 7 plus x. Again, this is where you sort of start getting to those edge cases and you think to yourself, you need to be a bit careful with how you use that. And in fact, there's quite a lot of detailed rules. If you read the JEP, there's quite a lot of detailed rules I don't have time to go through, talking about exactly how being complete and exhaustive works with these types of situations. So, puzzle number 4. Right, so let's say we mix things up a bit. So I've now got test obj, passing in an object reference, switch on O, case integer, wrapper class, I. Then I'm going to have case for primitive, byte, print out byte, and a default which prints out something else. What is the result of test obj integer dot value of 42? So who thinks we get integer? Who thinks we get byte? Who thinks we get something else? Ooh, okay, a few people saying something else. Interesting choice, because of course you're going to get integer. You're passing an integer object to the method. So the first thing it's looking at, is it an integer? Yes, it's an integer, so we get integer. All good. What about if we pass in 42 on its own? Who thinks integer? Who thinks byte? Who thinks something else? Not a lot of people voting here. I was hoping for more audience participation. Anyway, the answer is integer. Why? Because what's happening here is auto-boxing. Auto-boxing is because we have to pass an object reference in. 42 is a primitive, so we can't pass a primitive. So the compiler will say, oh, auto-box it. But this is where Java uses automatic promotion. So even though 42 will fit in a byte, it gets automatically promoted, first of all, to an int, and then boxed into an integer object. So that's why we match against integer. What about if we have byte.value of byte 42? Who thinks integer? Who thinks byte? Good. Who thinks something else? A few people. Well, the answer is byte, because of course, what's happening now is unboxing. We're passing in a byte object as a reference. The compiler then goes, okay, well, I need to test against an integer, not an integer because it's a byte. Test against a byte, well, I can unbox the byte wrapper class and get the value as a byte, match against that, and I get a byte. What about if we pass in short 256, where we're actually doing an explicit cast to a short? So again, who thinks int? Who thinks byte? Who thinks something else? Ah, good. Lots of people thinking something else. And the answer is something else. What happens here is the compiler says, right, okay, so we need to do wrapping again, so we need an object reference. But this time, because you have explicitly cast it as a short, the compiler will not do automatic promotion. It will say, you cast it as a short, so we will wrap it into a short class, short object, and therefore when we test against it, it's not an integer, it's not a byte, even if we unbox it, and we get default. Puzzle 5. Right, switch versus instance of. Okay, how long have I got? 4 minutes. Okay, Right, let's see if I can get through this. Right, so this time we're going to use our seal class, but in this case, we're going to make shape abstract. How about if I do this? So I'm going to have shape details, and this time I'm going to use instance of for triangle, square, and pentagon, and just call the appropriate method. I'll do the same thing, but this time I'm going to use a switch where I do case triangle, case square, case pentagon. And the question is, will these deliver the same behavior? And since I'm running out of time, I'm not going to ask the audience. The answer is, they will deliver the same behavior with one exception. And that is, in fact, the exception. Because if you call shape tester A on null, all you're going to get is shape details, because it will fail the tests in the instance of. But if you do it on shape tester B, which uses a switch, you get a null pointer exception. Puzzle 6, primitives with instance of. Right, so x is 42, and it's an int. If x instance of int, print out int. Prints int, very logically. If x instance of byte, who thinks that we'll print byte? Okay. Who thinks it won't print byte? It prints byte. 42 fits into a byte. So this is where, again, what we're seeing now is not just the compiler being involved, but also the JVM. So the JVM will actually say, okay, can I make x into a byte? And yes, you can. So it will match against instance of byte. Again, this is where those edge cases make this a little bit more challenging. If x instance of byte, print out byte. If x instance of int, print out int. Who thinks it's going to print byte? Who thinks it's going to print int? Not many people. Well, the answer is yes, it will print byte, because 42 still fits into a byte, so it will work. Switch them over. X instance of int, x instance of byte. What are we going to get? We're going to get int. It's the first match, not the best match. So even though it will fit into a byte, it will also fit into an int. So when we test against an int, it passes. Primitives we switch. Okay, so, yep, 1 minute 53. Int x equals 42. Case byte, case int. What happens? Byte, value is 42. So, yes, it will actually work in that case. That's because 42 will still fit into a byte. Case int, case byte, switch them over. What happens now? Domination. The label dominates, so it will always match against the int first. So again, this is the difference between instance of and the switch pattern matching. So int dominates byte. What about if you use a wrapper class? So going back to our integer, now byte. Then in this case, will it work? Answer is yes, because we're doing unboxing, or boxing in this case, into an integer, and it will work. X is 128, byte and short. Will this work? Well, no. Doesn't cover all possible values, because if you pass in something that's an int, as in a full int, then it won't match because there's a byte and short, but not an int. Completeness still applies with primitives. Even if we make that final, so the compiler could theoretically check that it would fit into there, no, that won't work, because the thing can only do so much. Quickfire final round. In the last 25 seconds that I've got, if we make x 65535 true or false, is it an instance of byte? No, because it won't fit in a byte. Is it an instance of short? No, because the biggest number you can store in a short is 32768. Instance of int, yes it is. Instance of long, yes it is, because of course that will fit in a long. Instance of float, yes, because you can represent any integer as a float. Double, same thing. And finally, Boolean, no, because incompatible types. Right, so just to summarize then, in conclusion, pattern matching, very powerful set of constructs, great fun, but be very careful of the edge cases. And with that, I'm going to say thank you very much.